All right, let's get underway here. There we go. Wrong slide deck. What's going on here? There we go. All right, so no details today. We're grading exam 3, and I think we've done 2 of the questions, and we'll start grading homework 3 or homework 2 as soon as we're done with that. Plan to post a question of the day later today. It's not quite done yet. So today we're going to continue with our discussion of parsing these texts, like we're going to look at War and Peace and Moby Dick and some other books from Project Gutenberg. And if you recall, we had gotten as far as changing common contractions and just simply choosing to use string replace to replace these occurring in the text with their expanded form. In a sense, we're reducing the problem to the simpler problem of parsing English that doesn't have contractions. We had come across with a read input, reads in the file name, creates a dictionary that has the frequencies of every word that we find in the text. And we do that by reading in one line at a time, lowercasing it, doing the replacement. Recall that every one of these is an XY pair. So we're going to do 92 calls to replace in that line whatever the value of X is with whatever the value of Y is. And then we're going to call our parsing function on that transform text, all lowercase. Close the file and return the frequency counter. Now, we did this by lowering the line up front. And if you recall, we did that so that in this parsing function, just ignore the stemmer for a minute, in the parsing function we could strip out all the punctuation on either side of the word for every word in the split text. So every word now is a separate string in a list of the text. And we would avoid all the words that were in the stop words. So we would just ignore a, the, and so on. And then we would just create this dictionary in D. If W was in D, we just add 1 to its occurrences. Otherwise, we just create it in the dictionary with a value of 1 when we find it the first time. And this is fine. The early lowering the file, lowering the text earlier means that I'm sure all the words are identified will all be lowercase. I won't mistake a word that has uppercase and lowercase as 2 different words because they're all lowercase. But it also loses information, as we'll see later, when we try to identify characters or proper nouns in the text. It lasts for 3 clicks and then it dies. I don't know. Everything's going to hell. Okay, so I told you to ignore the word stemmer. Oh, it's working again. I told you to ignore the word stemmer here, but let's talk about what this does. So I briefly mentioned last time that words in English often appear in multiple forms. So we know, for example, that giving and give are 2 forms of the same verb, to give, right? But the sense, the semantics of that word is identical. In other words, whether I'm giving something to you or whether I give you something, the same act is being described. It has the same meaning. So word stemmer are used by search engines to collapse words that have different morphologies, different forms, but the same meaning. So when I say morphologically similar words, that means that they are similar in form but not identical. So a really good example of this is when you have possessives, apostrophe S, Henrys as opposed to Henry. Or when you have plurals with the added S. That's another example of the kind of thing we'd like to do. And doing this, writing some functions that look at a word and reduce it to some canonical form That's really hard. I mean, this is what linguists think about all the time. However, what search engines have taught us over the last 20 years, since the birth of Google, 20, 30 years now, is that you can do really, really well with really simple, really stupid tools. In other words, they don't have to be super fancy or super good. You get 90% of the stuff done with something that, is actually just kind of hacked together. So we're going to look at some very simple stemmers. The simplest design for a stemmer is to simply make a list of all the words in War and Peace and identify each word with its canonical form. So giving maps to give, gave maps to give, has given maps to give. You just make a list, a big lookup table, and you transform every word to this simpler table. The problem, of course, with that is that if you build that table for the English language, it's going to be really, really big, right? You're going to have to, for every word, you have to look it up and translate it to its canonical form. Does everybody understand what I mean when I say canonical form? That's sort of the base form. So this is really a horrible thought to contemplate, especially since so many of these sort of transformations are rule-based. In other words, this notion of giving and diving is the same basic process. It just happens a lot in English. So what we're going to do is we'd rather reduce our stemmers to a collection of rules that do most of the job, and we don't have to store this giant dictionary of translations. We just have a little function that applies those rules simply. And that's the whole idea behind a word stemmer. So we're going to look at two forms of word stemmer, neither of which works particularly well, but both of which are more than adequate for things like search engines when you're trying to find out, you're looking for an article that mentions the restitution of the amphora from a particular museum to the native country where they came from. It's good enough. You can still manage to find the right thing. So this is the simplest affix removal stemmer. So let's parse what this means. An affix is the end of the word, the ending of the word. And mostly what this stemmer that was introduced in 1991 does is it changes those endings we're familiar with in English, IES, ABLE, ING, and so on. It handles those. And this is what it looks like. It's like 10 lines of code. Basically, it looks for, you call the stemmer on the word, and it looks at the last, and the order of these is important. Looks at the last three letters. If they're IES, and the word is not EIES or AIES. In other words, if these are the last three letters, but they don't follow an E or an A, then we're going to strip those last three letters, and we're going to change it to Y. So think here, stories becomes story. So now, just with this first rule, any word that has a plural, any Y-ending word with a plural IES becomes its singular form. Now, we lose information, right? We lose the information that we weren't talking about one story, we were talking about many stories, but that's okay, because the notion that it's about a story is the basic semantics we're after. So the next step is I look for a word that ends in ES, but not with any of these three endings here. And if I get that, then I just drop the S. So here, the word stores, like, I went to the shops or the stores, S-T-O-R-E-S becomes store, singular. So again, this is dropping the plural S, but not for words like shoes. So shoes does not become shoe. All right? Finally, if the last letter is S, and the word does not end in US, SS, or YS, then drop the S again. So here, I use the second rule to drop the ES ending, but here I use the word to drop the final S, that's generally the plural S, except for words like bus, right? Or truss, or whatever. So applying these three rules sequentially, notice that there's no else if, they're all ifs, does a pretty good job with English words. Now, sometimes you get some weird stuff, right? So, for example, the word flies, F-L-I-E-S, ends with I-E-S and is not in here, so it becomes the word fly. That looks pretty good, right? That makes sense. I'm trying to think of a word that dies. The word giving, G-I-V-I-N-G, The word giving remains giving, and the word give remains give, for example, right? So those are a little bit more problematic. So after 1991, people started playing with these stemmers a lot, and here's a more sophisticated stemmer. It handles a lot of these different endings. And by the way, the order of these endings here is alphabetical, I believe. Yes, they're just alphabetical. But what we're really interested in is you can see this an extension of the Harman stemmer, because this first one, this second one, and this third one, first one, second one, and the fourth one are the same clauses of the Harman stemmer. There's just one additional one for apostrophe S to possessive, which removes the possessive form. And then everything else is just reduction by these endings to collapse it, not to a word. The Harman speller gives you a word that's usually a legal word. Here it gives you really the stem of the word that sometimes is a little bit short. Okay, let's see how we do with this. If this is my old input form for War and Text. When I say look up isn't, I see there are 47 versions of the word, 47 instances of the word isn't. If I read them again with my new stemmer, with my new input, which has the stemmer and handles the contractions, as we said, I get an error because this word no longer appears in War and Peace. We know it becomes is not, and then is generally dropped by the stop word. Okay, so here's an example. So this gives us a really nice description of the kind. We've dropped the contractions. This doesn't really exercise the stemmer. But words like faith become fey instead of faith. There are some times that words just don't match. English is a really irregular language, right? There are languages where the rules of spelling or orthography are really straightforward. In Italian, when you say a word, you know how to spell it. The way it sounds is the way you spell it. I believe in Spanish, the way it's spelled is the way it sounds, but not vice versa. Any Spanish speakers here? Does that make sense? Is that about right? So you see the word, there's a unique way to pronounce it. In Italian, you see the word, there's not always a unique way to pronounce it. It depends on context. But when you hear the word in the right context, there's a unique way to spell it. The only language I know that is bidirectional this way is Esperanto, which is an artificial language that's designed to have unique orthography for sound and unique sound for orthography. Most languages are a mess, right? English is the worst of all, perhaps. And the reason is because English doesn't come from a single root language. It's a mix of the spelling rules from Anglo-Saxon roots, right, and from Romance roots as well. They're inconsistent the one with the other. That's why we get words like K-N-I-G-H-T for night, which makes no sense when you look at it and try to think how this should be pronounced. So handling English is actually harder than handling some other languages. Now you might wonder, how do Google and these search engine places do this today? Well, this approach that we're seeing here is the way search engines were first constructed, using these kind of rules to deconstruct words and find their semantics. Now we have different methods for doing these, which rely on having a very large corpus of data and using things like neural networks to capture sequences of words that have a certain meaning. So we map those words onto a meaning based on the way they're used, based on their context, how the context is formed. So those systems are very different than the kind of system I'm describing to you, which is sort of the roots of the early search engines. All right, so seeing how hard this is, we certainly don't want to resort to doing something. This is gross, right? I mean, you think of all these rules and implement them in code, and you have this list of 92 contractions that you're substituting. It's a terrible way to write code. Fortunately, there's this really good tool for doing this kind of thing. So we're going to take a day and maybe 2 days to dive into the world of regular expressions. And when I tell my friends in the department that I go through regular expressions in this class, they say, why do you do that? That's crazy. Regular expressions you would normally not see until you're after data structures and probably in the algorithms course. I think you will probably remember very little of regular expressions. but you will have seen them and you'll know what they are. And later you'll be compelled to learn about them more and actually use them in your code. But for now, I just want you to be exposed to these and see how regular expressions work. Regular expressions, in a sense, are really a separate language embedded in Python. So we have our whole regular expression language in Python. Just like we have a language for strings where a \n is a new line, there's a language for regular expressions that essentially set up a pattern matching system. So you can build regular expressions that match a pattern, and they'll say, yes, I'm the same as that pattern, or no, that pattern doesn't fit what my descriptor is. Moreover, these regular expressions don't just exist in Python, they exist in almost every other programming language. They exist in Perl, they exist in C, they exist in C++, they exist in Java, usually as libraries that you import. And by and large, the regular expression language is the same throughout, regardless of language. There are small syntactic variants. So the insight here comes from noticing that most of these really have a lot of similarity. And here, for example, the NT, N', could just be handled with the substitution for space not. So here's how we're going to take a look at a way of doing this in a uniform way, which is the regular expression language. And the way this regular expressions work is they describe patterns as strings with a whole bunch of special characters embedded in them. And this is why people hate regular expressions. They're very terse. There's a lot of sort of hinky syntax. You have to remember what the $ means when it appears in a regular expression. And that's why I'm saying you probably won't remember or assimilate a lot of this, but you'll know they're there. And when you have to write a regular expression, you'll go off and look it up and make sure you test your regular expression to make sure it works. I just want you to give a flavor for these here. So the basic idea of the regular expressions is they are just strings that look for matches in other strings. So the basic regular expression is, without any of these special characters, which you call meta characters, every character in a regular expression matches itself. So the regular expression ABCDE is exactly like the string ABCDE. So this is a match. If this is the regular expression or the pattern, and this is the text I'm matching the pattern against, the answer here is yes. They're the same, they match. The first meta character I'm going to introduce is the period. It basically says match anything. So every period in a regular expression matches any character in the text. So, accepted uline. So if I were to write ab.de as my pattern, it will match any 5-character string that starts with AB and ends with DE. So this pattern will match this string, but it'll also match ABXDE or ABYDE, whereas this first pattern here only matches ABCDE. All right, so the period is the wild card. The square meta characters, the brackets, are used to express the class of characters. So for example, if I change my pattern to be AB square brackets with WXYZ DE, this pattern will match any of these 4 strings, but no other. So in a sense, the period is like the brackets with every possible character between them. And the brackets are used to restrict the range of the match to just the characters I put in the bracket. Everybody with me so far? So far it's pretty straightforward. Now, I can take these character sets in the brackets, the character class, is I can use the caret meta character in the first position to negate the sense of this. So in other words, this pattern here and this pattern here are different because here it says match any characters except WXYZ, and here it says match only the characters WXYZ. So you can see with just a few meta characters, the brackets, the period, and the caret, we can already express some fairly powerful patterns that will match only certain string types. How many of you used regular expressions before? Anybody? Sometimes people who do web programming. Any of you? Yeah, you've probably used them to validate, for example, text and input in a web page. You want to make sure phone numbers look like phone numbers. This is the tool you use. All right. Now, so far we've done one-to-one matching of characters in the pattern to characters in the text. Now we're going to express repetition and iteration in a regular expression. The easiest meta characters for those are the asterisk, the plus, and the question mark. And these are modifier characters. They modify the pattern element that directly precedes them. So for example, the asterisk means 0 or more copies of this character. The plus means 1 or more copies of this character. And the question mark means either 0 or 1 copies of this character. So for example, AB dot question mark DE, we know that dot matches any character. But when I put a question mark after it, it also allows me to match ABDE where the character is missing. Because the question mark says there are either 0 or 1 periods. Period matches any character, but if there are 0 periods, then that allows it to match this as well. So the question mark modifies the character right before it. If the character right before it is just a simple character like the A, then it says either there's an A or there isn't. But if the character right before it is a meta character, like the period, then you have to interpret that meta character 0 or 1 times. Same thing for the plus, where you interpret that meta character 1 or more times. So for example, AB dot plus DE will match any 5, 6, 7, 8, 9, 10, up to however many characters you want, string that begins with AB and ends with DE. Because it says you can have 1 or more things in between them. In fact, there it is. So any string that starts with AB and DE, regardless of length, provided that there is at least 1 character. Oh, no, sorry, the asterisk means 0 or more. So any string that starts with AB or ends with DE, regardless of what's between those, the start and the end. All right, questions so far? So what have we seen? We've seen periods match any meta character. We've seen character classes with the brackets. We've seen character classes with the brackets negated with the caret. And we've seen the repetition characters, and we've seen that these things can all be combined and put together. Now, if you want to regulate how many repetitions you allow, in other words, here, this is fairly coarse, 0 or more, 1 or more, 0 or 1. What if you want exactly 3 copies? Or between 3 and 17 copies? Well, there's a meta character for that. Those are the curly bracket meta characters. When I see a curly bracket m comma n, and these are integers, that means that the pattern right before me must be repeated at least m, but no more than n times. Now, for you Python, now that I've indoctrinated you on Python beginning and ends and ranges, these are not Python range numbers. So in Python, we would start counting at 0. And end at, n minus 1. Here, these are actual integer counts the way your niece or nephew might count, starting at 1 and going up to and including the top number. So here's a regular expression that matches a US phone number. Let's see what it looks like. So we have a backslash parentheses. I'll skip that for now. We recognize these brackets here as a character class of all the digits. And I see that I have a curly bracket 3. When this appears without the n, it means it must appear exactly 3 times. So this is like an area code, 3 digits, backslash parentheses. We'll talk about that in a minute. There's a space here you can almost see. There's the digits again, 3 of those, a hyphen explicitly, another digits, and 4 of those. So this looks like something like, I should tell you what these are. Because the rounded parens also have a special meaning, as regular expression meaning, I have to escape those with the backslash so that I'm saying these are explicit parentheses. So this will match anything that starts with the left parentheses, has 3 digits followed by a right parentheses, a space, 3 more digits followed by an explicit hyphen followed by 4 more digits, which looks like a US telephone number. So this backslash, because these regular expressions are strings, the regular expression patterns are expressed as strings, we have the same mechanism to escape the special meaning of a meta character. Because the rounded parentheses is a meta character, we're going to escape it to make it a real rounded parentheses. Everybody see how this works? You can imagine how in a web page in JavaScript you might give a regular expression saying here's what a phone number should look like. And if somebody types in something that doesn't look like a phone number, it says, no, sorry, that's not it. Another example of validation of numbers, credit card numbers are validated, often with regular expressions, or can be. Now, I can make this a little bit more concise by introducing a new special character, the hyphen. Now remember, here I had a hyphen that is explicit. There's a hyphen between the first 3 digits and the last 4 digits of your phone number. That has to match a hyphen. But these hyphens are different because they appear inside the square brackets. So characters that appear inside the square brackets can have a different special meaning. Like the caret, it has a special meaning inside the square brackets. The hyphen inside the square bracket means that I can have any match, any character between 0 and 9 inclusive. Remember in the early days we talked about ASCII encodings? I think we did, maybe not. Did we talk about ASCII encodings in this class? So how all the letters appear in alphabetical order in ASCII, and how the uppercase letters appear in alphabetical order before the lowercase letters, or after, I forget which, doesn't matter. The digit characters also appear in digit order. So when I say 0 through 9 in the normal collating sequence, that means just the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this pattern is exactly the same meaning here. It's a little bit more concise. Yes?
How does Python know when you want to go into metacharacters?
Right. So the question is, how does Python know when I want to interpret this string with metacharacters? I've kind of glossed over that. You'll see how we do it in Python shortly. But this is just a string. It only becomes a pattern when I use it in a function that says regular expression, treat this as a regular expression. So regular expression patterns are just strings, right? But when you have a function that is a regular expression function that takes a pattern and an argument, that's when that string gets treated as a pattern. That's a good question. Everybody with me? Now, I'm introducing a bunch of different regular expression common special characters. In this case, we've gone from using explicit characters to using ranges, but we can do even better. I could just say \d to stand in for all of the digit characters. So a D in a pattern is just a D, but if you put a backslash in front of it, you give it special meaning. So remember, a backslash takes away special meaning from characters that have it, but gives special meaning to characters who don't have it. So a \d represents those digits. A \D represents all the non-digits, in other words, caret of 0 through 9. \s is all of the whitespace characters. The whitespace characters are tab, new line, carriage return, I forget what F is and I forget what V is. These are like end of page or something. These are all the special codes that regulate carriage control in the ASCII alphabet. And they're all treated just like spaces, like white spaces. \S is everything but those white space characters. When we use the split method in string, remember the split method that breaks apart a string into a list of words? It uses these white space characters to decide where to split. So it's the same concept. And finally, \W or W, these are the alphanumeric characters, which are A through Z lowercase, A through Z uppercase, and 0 through 9. So I could use this to recognize all the characters that might go in, say, your password. If we're not going to have special characters or punctuation, we're just going to have numbers and letters, I could use this to say your password must be made up of \W star characters. All right, so let's review what we've seen. We've seen the predefined character classes where it's your backslashed ASCII letters. We've seen character classes with explicit brackets and with carets to negate them. We've seen the meaning of the hyphen to specify a range in a character class. We've seen period as the match wildcard, match any meta character. We've seen plus, question mark, and asterisk as the repetition characters. And we've seen the curly bracket notation for explicit repetition counts. That is the sum knowledge we have of regular expressions. It is just the very basics. Because the regular expressions language, which is a language, which you express as a string, you can think of this string that is your pattern as a program. Right? That string is something, it's like a program written in a single string that is interpreted by a regular expression interpretation engine, and it runs this little program against a target string. And if the program executes all the way through, then we have a match, and if the program fails part of the way through, then we don't have a match. We can see this with the example, oops, sorry, I'm going the wrong way. We can see this with the example with the phone number. If I think of this as a program, and I had written separately the string containing my telephone number, I can think of this program as being executed left to right. Is there a left parentheses? Yes. Is there any one of these characters? Yep. Does that repeat 2 more times? Yep. Is there a right parentheses? Yep. So as I parse this left to right, I run it against my target. And if my target text is successfully run against the pattern, then I output a yes, saying this pattern matches that output. Sorry, this string matches that pattern. All right? So think of this regular expressive language as yet another programming language you have to learn. So this process of running a regular expression pattern against a target string is done greedily. And it has that same backtracking character we had when we wrote Boggle and looked for all solutions on the board. We would try every possible alternative and see how far we could push each direction. The same kind of thing happens here. So let's assume that this is my pattern, in other words, my program. The program says find an A, find one of these characters as many times as you like, and find a B. So this says match any string that starts with A, ends with B, and has these characters in between it. And I must mention that when you're using regular expressions against character string targets, the regular expression can successfully run against a target without consuming the entire target. In other words, when I'm matching my telephone number against some text that starts with the telephone number and then has my name attached to it, that's still successful. It just won't consume the whole string. It'll get through the phone number and says, well, that's all my program asked for. There's a phone number. We're ready to go. And it's successful. So here, let's see how this matching might work. So the first A matches the A in the string. That's good. A, B, C, D star, I'm going to say how many of these B, C, Ds can I match? Well, there's a B, a C, a B, a D. So I'm going to suck in as much of the string as I can when I'm given this directive. So that's what I mean when I say pattern matching is greedy. Every character in the pattern will be matched against as much of the string as possible. So A matches A, B, C, D star matches the whole pattern. And then I look at the last character and this fails because I'm done with the string. There's nothing left there. So it looks like this pattern doesn't match the string, but you and I know that if we look at this sort of from our perspective, we can see that this A, B, C, B matches this pattern. Just ignore the last D, but the first 4 characters will match this pattern. So how does a pattern matching engine find that if it just failed by doing this greedily? So it sucks in as much as it can and it fails. So what it really does is it says, this fails, but I used as much of the string, I consumed a lot of the string with this previous directive. So I'm going to back up a step and I'm going to consume one less character. So in the first case, the BCD star consumed BCBD. Here, I'm going to let it just consume BCB, so one less character. Unfortunately, if I proceed from there, that still fails because the last B in the pattern doesn't match the D that's left here. So I've had 2 failures by pushing as far as possible and then backtracking and trying a new ending. That didn't work either. So I'll backtrack one more time and let this BCD star match one less character than before. So first time it matched all 4 characters, second time it matched 3. Now it just matches 2. And this time when I resume my pattern matching with the B in the pattern, I get a match. And so this pattern matches the first 4 characters of this string, leaving the D unmatched. So this pattern matching process involves sort of interpreting the pattern alongside the string and interpreting as much of the string, consuming as much of the string as you possibly can. If you fail, you back off your assumption of consuming as much as you can, consume a little less, and see if you can push that through. And if you can't, you back up a little more and push that through. If you've ever seen those little bumper cars that navigate in mazes where you hit the wall, they just sort of back off and try a different direction, it's sort of that idea. When you run out of string because your pattern doesn't match, you back off a bit on the interpretation of the pattern and try again. You keep trying to push it through. The net result is that the pattern matched against the string, if it matches successfully, it will have matched as much of the string as is possible. Right? We can look at this, you and I can look at this and say, well, this asterisk means it doesn't have to match any of that. So in fact, the first 2 characters are also a match for this pattern, but we'll never see that because we'll always try to find the longest pattern that matches. And this process of using as much of the string as possible and then backing off and resuming ensures that you'll match as much of the string as you possibly can. Are there questions? So we've seen a few meta characters. We've seen how patterns, regular expression patterns, are really like little programs that are interpreted by this regular expression engine, and the interpretation of the pattern is run against the target string, and the result is the longest possible amount of string that matches the pattern. So that's the takeaway for today. Okay. So as I mentioned, this is a backtracking search because when I run out of match, I back up and try the other branch that I left suspended. Okay, so now let's try to answer your question about how do I use these in Python. And you'll notice, first of all, that I'm using re.match. This implies that it comes from a module called re. So what I've done offline here is I've imported re, which is the regular expression engine. Now, many times when we import stuff in Python, we would say from re import star, and then I wouldn't need to preface every function from that regular expression package with re. It is common practice, and one I subscribe to, that when using regular expressions, we just import the regular expression module, because the extra 2 characters remind me, they serve me as an important reminder that this is sort of that magic regular expression stuff. Something that just says match doesn't evoke regular expressions to me. So how does this work? Well, here is regular expression match. That is my pattern, AB star. This is my string, ABC, ABB, ABD. And I get back a regular expression object. This is an object, an instance of the SRE match class that has a value AB. So in other words, it's matching the first 2 characters. And as part of this object, it also tells me where it found those 2 characters. So this AB star, the longest match I found was AB, starting in 0 and ending in character 2. So regular expression match starts matching in the very first character of the string, goes as far as it can while matching this pattern. And if it finds a match, it will return a special object that tells me how much I matched and where and from where to where. Regular expression match will always start at 0. Let's try it again, this time with the pattern CA star. And even though there's a CA here, this returns nothing. The reason it returns nothing is this regular expression match needs to start matching at the beginning of the string. Kyle, yeah, go ahead. Yeah, so I think the question, is, I barely hear, but I think the question is, once I match this, could I say, okay, starting from 2, does it happen again? So can I iterate the search looking for multiple copies like you might in a word processing system? And the answer is to have functions for that, right? I'm just showing you the two basic functions today, regular expression match and regular expression search. And there are features. You can write Microsoft Word with regular expressions, right? When you are searching for text in your essay or your writing assignment, you are essentially using something that does this kind of search. You're generally not searching for regular expressions, although some word processing systems, instead of just letting you search for certain strings, will let you search for regular expressions. You mostly use Word. People use Word. Is that right? So when you do, I think it's Control F or something to find in the document, you're often given a little box and says, do you want to search only for whole words? Or does case matter? And you click on case doesn't matter or just whole words. Well, deep down inside, what Word is doing is it's setting up a regular expression that says it's got to be bounded by white space. That's how you get whole word characters. Or case doesn't matter, and I'll show you how to do that with regular expression match. And so in a sense, you get a sense from your interface that you use in Word what's actually going on underneath the hood, and now you're seeing it. Okay? So we've seen regular expression match. Regular expression search searches throughout the string, starting from the beginning. If it fails, and there's no way to proceed from the beginning, it tries from the first character, then from the second character. So this second match with regular expression search would have found a match in characters 2 through 4 in the Python sense, and would have reported the match. Oh, well, here we go. Regular expression search doesn't find this starting here, doesn't find it starting here, but does find it starting there and says, I found a CA that matches from 2 to 4. Okay? So starts matching at the beginning of the string only. Search repeats that match until it's successful. Now, if I'm using RE search instead of RE match, and I want to express a pattern here that is anchored either to the beginning of the string or the end of the string or both. In other words, does the entirety of my string match regular expression this with regular expression search? There are special meta characters, the caret and the dollar, which anchor and mean beginning and end of the pattern I'm searching. So think of regular expression match. I can get the behavior of regular expression match by using regular expression search and putting a caret at the beginning of the string, because that says this pattern is anchored at the beginning of the target string. But I have a similar anchor that I can put at the end of the string, a dollar sign, that ensures that the whole string is consumed. All right? Regular expression match is always anchored at the beginning of string, but doesn't necessarily consume the whole pattern. Regular expression search is not anchored at the beginning or the end, but can be using these special anchors. So, if I do this regular expression with regular expression search, it says, look for my phone number, look for that phone number, and make sure that it consumes the entirety of the entry. So imagine that you're writing a web page where somebody has to enter their phone number. You want to make sure that what they enter is exactly the right format for a phone number and contains no extraneous characters either before the phone number or after. I'm going to anchor it with a caret and a dollar sign. But in these character class brackets, we saw how the hyphen has one meaning outside the bracket. It is just a hyphen. But inside the bracket, it pertains to a range of characters. So we know that when characters move inside the square brackets, they sometimes change meaning. In the case of hyphen, it goes from a plain character to a special character. But here, what's a special character outside the brackets becomes an explicit plain character inside the brackets. The exception here is caret, which inside the bracket has the negation meaning and outside the bracket has a beginning of string meaning. So if I wanted to define a character class that had an explicit caret in it, I've got a problem, because caret inside means negate and outside means beginning of pattern. And the solution to the problem is that the caret means negate only if it's the first character in that sequence. If it's anywhere else in the character class, it's just a caret. That is an ugly way to design a language. These characters have meanings on meanings on meanings that are based on the context in which they appear. The answer to that is, yeah, it really sucks. It's a terrible way to design a pattern. But it's extremely concise, and you just sort of have to suck it up and get used to it, because this is what regular expressions look like. When you get to algorithms and later to theory of computation, you'll recognize that these little regular expressions really are implemented as finite state automata, and that there is an interpretation that can be made into a very efficient computational engine to match that string. And that's what makes them so powerful and useful. So, caret ABC means anything except the characters ABC, because the caret is a special character in the brackets. But ABC caret means only match characters ABC or caret, because the caret is not in the first position. AB through Z means match any characters A or B through Z, but ABZ hyphen, like the caret, the hyphen is no longer a range when it appears at the end of the character class, because there's nothing behind it, nothing past it. It's just the way it is. So we have to import the module RE. The regular expressions, when they are matched, return regular expression objects. Objects are instances of classes with all sorts of cool methods for manipulating those objects. And each of those objects contains information about the regular expression that you matched and how or what it matched in the target string. If they successfully match, they will return an object of type RE. If there is no match, they return nothing. All right, I think this is a good place to stop. We'll talk about compiling regular expressions for maximum efficiency next time, and then we'll look at some regular expression examples and see how useful these can be when you're parsing English text. And good luck with the interview today. Who are you interviewing with?
Oh, I actually had my interview this morning.
How'd it go? Take care.